I will talk a bit about what we do for Earth system modeling. Originally, I thought I'd talk narrowly about clouds and convection. I'll talk a little bit about clouds and convection, but I think I made it a little bit broader than that. And this is a large group of people. Some are named here, and there are others building an Earth system model. This is a simulation a few weeks ago, or a few months ago, of the CliMA model at 32-kilometer resolution. And I'll tell you a little bit about what's in this model. Yesterday, we talked about ML methods and what they can do and perhaps what they can't do. And I thought it's useful to start with talking about what the problem is we want to solve. I mean, you all know Earth has warmed about 1.3 degrees. These are 5-year averages, 1.5 degrees if you don't take 5-year averages. The question is, how much warmer will it get? And the question is pretty interesting in various facets. Number one, the warming we have seen is not all warming that could have occurred in the following precise way. This is from the latest IPCC report. What it shows is the left bar is the total human influence on global mean surface temperatures, just a little bit over 1 degree. The red bar is the effect of greenhouse gases alone that we would have expected on the temperature, which is already 1.5 degrees. This was several years ago. And the blue negative bar are offsetting human effects, and these are principally aerosols, air pollution, that cools the planet. And now the implication of this graph is, so number one, if you focus on the blue bar, it has a large error bar, and that error bar has increased over the last few years. It includes 0, and there have been recent papers, I say something about in the next slide, that this error bar now extends to -1 degree, potentially more. We simply don't know how large this cooling is, which means we all hope that we get to a world where we get to net zero emissions or near zero emissions, and one ancillary benefit of all that will be cleaner air. And that's something we should all celebrate. Air pollution kills something around 8 million people per year prematurely. We should wish for less air pollution. However, if you have less air pollution, that warming that currently is masked will be realized. And it's certainly important for us to know how large that warming is, because that very much determines our climate future in the next few decades. So that's one piece. And I think Marcos in some fashion already talked about it. So the problem here is aerosol effects on clouds. These are ship tracks, shipping lanes, and you see the ships make clouds wider where they pass over the ocean. And there have been a number of interesting papers in the last few years that try to estimate the aerosol effects, the aerosol cooling effects, and especially the effect on clouds, as opposed to the direct effect of scattering of sunlight by aerosols. They come up with various numbers. These papers were written fairly carefully, and they always come up with numbers like -1.1 watts per meter squared, and for the uninitiated, you probably don't know what this means. But if this is right, -1.1 watts per meter squared is profoundly scary. It means there's more than 1 degree of warming currently masked that would be realized as soon as the air gets cleaner. This is on top of the direct reflection of aerosols by sunlight. So we don't know if any of these estimates are exactly right. Probably none of them are exactly right. But the point is, this is the type of thing we need to constrain. So climate change is certain, but the magnitude of changes is not. This was aerosol effects that Marcos has worked on, talked a bit about. Here is now a spaghetti graph, likewise from the IPCC report, of the warming produced by various climate models that contributed to the IPCC over the next few decades from a little bit back. And there are 2 emission scenarios, orange a higher emission scenario, blue a lower emission scenario. And if you say focus on the 2-degree warming line relative to pre-industrial levels, and just look at various models cross that line, the estimates vary by 50 years or so. So this is not useful for engineering purposes. If you design infrastructure, you want to know when will it be 2 degrees warmer or how much warmer will it get, and you look at these kind of graphs and it's all over the map. So this is, aerosols play a role in this. The other part that plays a role is the equilibrium climate sensitivity, just the response of a climate system to mixed greenhouse gases. We heard yesterday the big problem were small scales, clouds paradigmatically the most important of them. Almost more than half the spread in these model predictions is due to clouds, and specifically low clouds over tropical oceans, like these stratocumulus clouds in the lower right, for example. They have dynamical scales somewhere between meters to 100 meters, and climate models have resolution typically 100 kilometers, maybe going towards 10. In Europe, there's a big effort to get to kilometer resolution. Even at a kilometer resolution, you're not even close to resolving the dynamics of the clouds, and you're certainly not even close to resolving the microphysics. So we have to do something about the small scales, no matter what. So here are the questions we need to answer, we as a field need to answer in climate modeling. So number one is, what is the effect of greenhouse gases on the climate system? What is the equilibrium climate sensitivity? That's sort of a canonical yardstick, the equilibrium warming in response to doubling CO2 concentrations. The big unknown is how clouds will respond and alter Earth energy balance. If you want to build a model that you can legitimately call a climate model, you need to have an answer to that question. And in fact, that's Manabe, 1965, 67, won a Nobel Prize. That's the types of question Manabe answered. And then a little down the line, you want to have an answer to a question of how aerosols modify climate. How will changes in aerosol emissions impact climate? And the challenge is to quantify how aerosols influence cloud formation, indirect effects of aerosols. And once you have that, you probably also want to say something about the carbon cycle. So right now, the terrestrial biosphere takes up something like a third of the carbon we're emitting. So this is carbon that's not going in the atmosphere. It's not modifying climate. It's taken up by the terrestrial biosphere. We don't quite know where. We don't know how this will change in the future. If you want to say something meaningful about climate change for the next few decades, you need to say something about how the terrestrial carbon sink changes as we go forward. I would say these are the top 3 questions. You can add more questions, but I want to list them and be explicit about it, because if you have a model that doesn't have a viable path to answering these questions, you can call the model an emulator, you can call it a weather emulator, you can call it a weather forecasting model, but don't call it a climate model. It's not a climate model. This is what any climate model needs to be able to try to do, at least. I think that's useful to keep in mind when we talk about what machine learning can and can't do. If you try AI-only climate modeling, I think you will not succeed at answering these questions. There are various reasons why not. One is confounding effects. If you want to quantify the effect, how clouds will change with climate, there are temperature effects on clouds from changes in surface temperature. There are direct radiative effects on clouds from changes in radiative fluxes. If you put more CO2 in the atmosphere, you change long-wave fluxes, that affects clouds. And then there are aerosol effects on clouds. If you look at the data we have, all of these things are mashed together. Things were changing. It got warmer while greenhouse gases increased. Aerosols changed. It seems impossibly hard to deconvolve those effects in observational data, and yet you must deconvolve them if you want to predict the future here. So I don't see how you could do this by learning from data alone. Never mind that, say, the gold standard that is being used in weather forecasting, ERA 5, or your favorite reanalysis data product, they're just as bad as climate models in simulating clouds. Tropical low clouds are not important for weather forecasting. They're poorly represented in reanalysis data. It's not even useful to try to begin with reanalysis data to learn about clouds, because the reanalysis are strongly influenced by a weather forecasting model that is just as bad as a climate model in producing low clouds, for example. How AI has worked for weather forecasting is by supervised learning, by solving regression problems. So you can schematically write it like I did here, that there are some turbulent fluxes that are unresolved, or you have some quantity Q, specific humidity or temperature, whatever it might be, and you're learning the mapping from the state of the atmosphere, involving humidity, temperature, whatever it is, to the tendency, the time increase in that. And we have no ground truth for those increments from observational data. That's just why reanalysis data are so widely used. They provide you those rates. That's useful for learning weather forecasts, but say for the clouds, we don't have access to these rates from any direct data. AI-only models obviously have problems with out-of-distribution generalization, sometimes with stability, and there is no AI model right now trained on data that can even do the most basic thing that Manabe did in 1965, which is predict the response to increases in CO2 concentrations. You can do it again if you train an emulator of a climate model on an existing climate model, but that's not making a climate model better. That's just compressing output from a climate model. That's useful. As Noah mentioned, that's extremely useful, right? But it's not making the climate predictions better. So where are we? So climate model needs to reproduce the present climate, but it can't stop there. If you ask how well do climate models do in reproducing the present climate, here's a bit of a history over the last 20-some years, going from CMIP 3, so around 2000, CMIP 6, so it's about almost a decade ago by now. The models, AMIP is the Atmospheric Model Intercomparison Project, so this is not including a coupled ocean, but prescribed ocean temperatures, but a coupled land. And here are 3 metrics that I think are useful. There are more you can pick, but these 3 are particularly useful. Precipitation rates, long wave and short wave fluxes at the top of the atmosphere. Energy fluxes at the top of the atmosphere are the beginning and end of it all in climate modeling. Climate change is fundamentally a perturbation of the energy balance. You need to be able to predict changes, small changes in the energy balance, order 1 watt per meter squared changes relative to a total solar irradiance of 1,340 watts per meter squared. So very subtle changes in the energy balance you need to predict. So you can ask how well do models do in reproducing the energy balance and precipitation rates in this case. Precipitation is good because it depends on almost everything. You can't get precipitation right without getting a lot of things right. So it's a good integrated metric. And the long wave and short wave fluxes, energy fluxes are good because this is the driver of the climate system. So this is a root mean squared error here. Each quadrant in a square is the season, March, April, May, June, July, August, and so forth. And the errors are normalized by the median over the CMIP 3, CMIP 5 generations. So red is worse, blue is better. And the good news is you generally see more blue on the right. Climate models have gotten better. That's good. The rate at which they have gotten better, I think is a little disappointing. It's order 10% per decade if you translate these numbers into a rate. It's not bad, it's definitely progress, but it's not leaping forward. The middle block are from what was called high resolution simulations. High resolution is always a time-dependent statement, so it's high resolution a little bit ago, 130 to 25 kilometer resolution in the atmosphere. This is just one model. In the paper where this was published, we had more models. The point is that these high resolution simulations are better, it's more blue. And, but crucially, they just go to 25 kilometers, not kilometer scales or anything like it. So this is computationally, right now, actually entirely feasible to do the simulations routinely. And then the right block are kilometer scale models. This is IFS and ICON. These are shorter simulations because these simulations are so expensive, we can't run them for very long. So it's 4 and 5 kilometer resolution simulations in this case. And the left column here, let's see, which one was it? Okay, this column here is just essentially the same column as that, just subsampled to a shorter period, which has more internal variability to make it directly comparable because these are shorter simulations. Point is, even at a kilometer resolution, you don't necessarily do better than, this is the median of the CMIP 6 model. Say for precipitation, ICON is worse than the CMIP 6 median. IFS is a little bit better, but there isn't any leap in accuracy. So going to kilometer scale resolution is immensely expensive, but it gives perhaps some benefits here for short wave fluxes for IFS, but the benefits aren't enormous.
How are the ground truths measured here?
So the precipitation rates are, it's a satellite-based product, and the long wave, all of these are satellite-based products. So long wave, short wave, there's a standard product from Ceres, EBEF, and precip is iMerge. So it's against observations, is to keep real observations. But actually, if you, maybe one thing to point out, these errors are quite large, right? The medians by which this is normalized are, it's like 12, 18 watts per meter squared in energy fluxes. And doubling CO2 is a perturbation of 4 watts per meter squared in energy fluxes. So these errors are larger than the signal that we want to predict, which doesn't mean you can't predict the signal, but the errors are still large. So if you compare this against other data products, it will look very similar. The errors are large, no matter what you compare it against. The seasonal cycle we have, and the seasonal cycle is is useful because it is actually, in much of the world, a large seasonal perturbation of the system. It is something we should use. Here's just one example. This from the carbon cycle, to take something perhaps that others won't talk that much about. This is from a paper in Physics Today a few years ago. What it shows is CO2, the seasonal cycle, just averaged over a few decades. In CMIP 5 climate models, there weren't too many that provided a carbon cycle in Alaska. And it shows just the average over the seasons. And you see in colors are the different models, and black are the observations. And the key point is that the amplitude of the seasonal cycle in the models is almost a factor 2 different for some models from the observations. So these are large discrepancies in the carbon cycle. And the colors of the models correspond to how much they change their global carbon uptake under global warming. So there seems to be a correlation between seasonal cycle amplitude and the response of the carbon cycle in these models, which is to say, trying to get the seasonal cycle right is a good first step towards getting the response to the long-term perturbation right. It's not a guarantee that you get the long-term perturbations right, but it's a good first step. So to predict aerosol changes, responses to climate, to greenhouse gases, I think physical guardrails are essential for various reasons. I mean, number one, it is just the one way we know how to predict effectively out of distribution. Perhaps even more importantly, we want predictions to be used. We want people to act according to what we predict. And you can't expect people to act on the basis of something that you can't interpret. There needs to be a plausible causal story. And what physics gives you is a way of providing that causal story. Also, climate simulations are long-run simulations, so 10 to the 7 time steps or something like that, typically, 1 million perhaps, meaning that the energy budget of the model needs to be closed if you couple it to an ocean and want to run it forever. It needs to be closed essentially to 32-bit machine precision, right? So 10 to the minus 7 times 10 to the 7, something like that, to avoid order 1 errors and drifts of the model into hothouse or icehouse states. And again, that at least the energy balance needs to be represented in some fashion. Mass balance would also like to be closed. And in the end, you like to predict the response to perturbations in the energy balance. And you want to be able to trace through that perturbation through the system. So I think it's very helpful to have a representation of the physics to be able to do this tracing through. So you want a trustworthy model in the end, and statistical skill is a necessary condition, but it's far from sufficient. So here's what we do to make progress. I talked a lot about physics because I think it's important. However, obviously, there's a lot of data. Obviously, the tools from the data sciences, ML, machine learning, have been tremendously successful. And I think what I wanted is a best of both worlds here. Use physics where you can, where it makes sense, but let the data speak where essentially physics reaches an end. So at CliMA, we've built a full Earth system model that has all these components in the pie chart, except for the land ice. So we have an ocean model, land model, sea ice model, atmosphere model, and so forth. And it has AI ML components embedded in various parts. And I could give you abstract principles how to do it, but it's perhaps best to give concrete examples how to do it. I mean, in some ways, the abstract principle is use physics, use process models where we are on firm ground with them, where we are confident that we know what we're doing with them, and let the data speak where that's no longer the case. And I'll give some examples what this means concretely. We use a hierarchical calibration process. Marcus talked a bit about it. We pre-train ML models in various forms, for example, on large eddy simulations, and fine-tune it on global data, and I'll show you an example how. And what I think is unique about what we have built is a model that we call it calibration-driven model development. We calibrate every week. You look at what's wrong, look at correlation structures of parameters, update the model, and do it again. And to do this in an automated way, it's essential that you have a GPU-native software stack, which makes it possible to run large ensembles pretty cheaply. The goal is to answer the critical questions I mentioned. What's the equilibrium climate sensitivity, aerosol cloud interactions, what's the fate of carbon in the terrestrial biosphere, and so forth. So climate is a really different problem from weather forecasting. Climate is about predicting the statistics of the system given changes in boundary conditions or atmospheric composition. Weather forecasting is mapping a state of the atmosphere right now to a future state. Weather forecasting is essentially deterministic. Climate prediction is essentially stochastic. It involves probabilities. It involves statements about mean temperatures or the probability of precipitation exceeding a threshold and the like. All of these are statistical questions. So the loss function you want to minimize for climate schematically looks like this little thing L I wrote there, where Y are observations, G of theta is your climate model. Theta is a bunch of parameters, and these parameters are physical parameters, ML parameters, can even be resolution parameters, anything you want. And notably, there is no initial condition in G of theta. The initial condition is a nuisance parameter. The initial conditions matters a bit, say ocean, cryosphere, the ice initial condition obviously matters for what happens in the next few decades, but the atmospheric condition is irrelevant for the climate prediction problem. So you want to minimize a loss that looks somewhat like that, and the angle brackets are averages, for example, monthly averages, so time averages. So the loss function involves whatever statistic you want. Y can be any statistic of a climate system you choose. It can be a complicated statistic, like the frequency of exceeding 5 inches of daily rainfall in Los Angeles, whatever it might be. It doesn't just need to be first or second moments of a distribution. It can be higher order moments, complicated statistics. And what you want is minimize a loss that penalizes a mismatch between simulated and observed statistics. That's fundamentally the problem in climate prediction. That's what society is asking from us, climate scientists, as a field. Give us the probability of rainfall in LA exceeding a threshold so I can right-size my stormwater management infrastructure and the like. Now, as always, ideally, you would want to minimize the loss function over unseen data. And of course, the challenge is we don't have data for the future, so we don't have a good validation case here. So we'll start with what we have and minimize the loss like that. Now, the problem is, this loss function is involving statistics. Statistics are noisy. They're noisy because of chaotic variability in the climate system. Here's an example of a loss function like that. It's from a paper by Rebecca Gini and Matti Mortzfeld at UCHC that we worked on together. And it just shows the loss surface. In this case, it's from a Lorentz system where it takes its statistics. And it shows, for example, one gradient-based method, the brown one, it gets stuck in local noise-induced minima. Every gradient-based method will, stochastic gradient descent will get stuck. And the other colored dots are various variants of common inversion. Common inversion has a nice smoothing property. It has a mean field property that smoothes the loss function just the way you would want to. It finds the right minimum, as in what your eye sees as the smooth minimum of that function. I'll talk a little bit more about it. So your standard off-the-shelf AI tools will not be able to solve this problem. Yeah.
What is the particular gradient-based method in this example?
This is a simple convex problem. This was just a Levenberg-Marquardt algorithm, but this is generic for any gradient-based method. And the others are various variants of common inversion. There's a transformed ensemble common inversion. There's an unscented common inversion, and the details maybe we don't need to get into.
So there's have you tested, I guess for this example, did you test anything that's momentum-based or like Atom, where they have running averages that kind of also smooth out that loss surface?
We have tried, so there are momentum-based accelerators actually in some of these other methods as well. We can talk about the details. It won't solve that problem for the gradient-based method. So what we do to deal with this problem is a 3-step algorithm which we call Calibrate-Emulate-Sample, and I think Marcus mentioned it. I think we should have called the first step something else, but let me explain what it is. So the first step is using ensemble common inversion. Ensemble common inversion, or variants thereof, we have many variants we have tried. This paper Rebecca is kind of a bake-off of the best method for a given problem, depending on parameter, space size, and such. What common inversion does well is put points. Points here are pairs of parameters and output y, theta and y, in parameter space in a way that places the points near the posterior optimum. This is what common inversion essentially does. So it's essentially solving an experimental design problem. You have a high-dimensional space, hundreds of dimensions potentially, and it places points in the space near where you would want to place them, say the posterior maximum. It scales well to high-dimensional problems. We know it from weather forecasting. It's used for billion-dimensional problems. So the problems in climate are perhaps hundreds of dimensions. Marcus showed some dozens of dimensions. It scales well with dimension, and the complexity is essentially linear. We called it Calibrate, and I think a better name would involve something with experimental design. I'm not quite sure what the good name is, but the point is it puts points where you want them to be in the high-dimensional parameter space, much more effectively, say, than Latin hypercube sampling, which suffers a bad curse of dimensionality. Then we emulate the map from parameters to terms in the loss function. You can use any number of emulators you like there. We often use Gaussian processes or something called random feature models, which is a more scalable version of Gaussian processes. You can use neural networks and the like. And then you sample the emulator in much the same way that Marcus talked about. So this is sort of a workhorse algorithm we are using. What you get out of it is parameter estimates. And again, the parameters can be neural network parameters. I'll show you an example of neural network parameters. That's roughly 1,000 times faster than brute force MCMC, simply because ensemble common inversion is very efficient in high-dimensional spaces, much more efficient than MCMC would be in exploring high-dimensional spaces. The emulators are fast to evaluate, so if you use MCMC on the emulator, it's very fast. It basically costs nothing compared to the first step. I stuck this in while people are talking before. You can include structural error models in this approach in much the same way. I think there is a good way of doing it. So the classical paper on structural model errors is Kennedy and O'Hagan, 2000, thereabouts. And what they did is they put a structural error model in the data space, so in the space of the y's in my notation here. But that's not where the error is being made. The error is somewhere made inside this G thing, inside the climate model, that you get something wrong about small-scale processes. So a better way of incorporating errors is internalize them in the model, have structural error terms inside the model. And the nice thing about this framework I outlined is that essentially it treats learning as an inverse problem, which means with proper regularization, you can learn anything, including structural error models. And we demonstrated with a few approaches, for example, with dictionary learning, with sparsity constraints, and neural networks, you name it. You can use just about anything there for structural model errors. There's a few lessons that after the fact are obvious, but were not obvious when we started. For example, you don't want to include a structural error model just because you can. You want to include it because you have to, which means that you don't want to include a non-zero error that doesn't project onto the loss function, right? That can easily happen. So you want essentially L1 sparsity constraints on these error models. It turns out to be important. Otherwise, you have error models all over the place that don't become useful anymore. So it's a few simple lessons like that, which are in those papers, but don't want to dwell on it. The nice thing about internalizing the model errors is that you can physically interpret it in the end. You can take apart this error model and try to make your physical model better where these errors were made. It's easier to interpret and so forth. So let me give you an example. For turbulence, clouds, and convection, what we do is the following. You take the equations of motion and you coarse grain them. So standard homogenization. And you get equations that look like that, and we don't need to dwell on what exactly they are. The top is like a continuity equation. A is some area fraction. So what we do is you coarse grain the equations over subdomains of a grid cell in the climate model. And you can write equations for these subdomains, and you can do this exactly. There's no approximation involved. Of course, where all the approximations come in is the stuff appearing on the right-hand side. You coarse grain, so you get unclosed terms on the right-hand side, as always, that you need to do something about. So there are these closure functions, for example, representing the exchange of mass between a cloud and its environment. Turns out to be a hugely important thing, called entrainment, detrainment. Those functions appear on the right-hand side. A priori, we don't know what they are. So then what we do is what in some ways has been done in fluid dynamics since Prundel's times for more than 100 years. You reduce those functions to non-dimensional functions of non-dimensional groups. Whatever the groups that you think are universal for this particular case. I mean, for entrainment, detrainment ends up being 6 non-dimensional groups that matter. And then you learn those functions from data. I mean, in a way, this is what fluid dynamics has done for more than 100 years, not with machine learning, but by reducing the turbulence near the surface to a universal set of functions, one in Overkopf similarity theory, and then someone goes out and measures those functions over a wheat field in Kansas in the summer of 1968, and those functions we all use in our climate models everywhere, not just in Kansas, and because they truly are universal. Same idea here. So those functions on the right-hand side are good targets for machine learning, and that's what we do. And again, we treat machine learning as an inverse problem. You can learn those functions from indirect data. We can't measure those functions directly. That's the hard part. But we can measure the effect those functions have, say, on cloud cover. So we generated a large data set, starting first with 500 LES from Jerry Shen, and then collaboration with Google. This has become 8,000 LES now that you can all use. I didn't put the link on the slide, but if people want to know, I can show you where they are. We use that for pre-training, the cloud prioritizations. And as Marcus said, that's a good first step, but not the final answer necessarily. I can show you some results. So the key to success here was the physical structure more than the machine learning. I'll show you a machine learning example in the next example. But here's 2 very different cloud and boundary layer regimes. So the vertical axes are very different. On the left, it goes to 300 meters, 3 kilometers, and 14 kilometers on the right. So there's a polar boundary layer with a very, very shallow inversion. It's a stable boundary layer, notoriously difficult for climate models. And colors are 2 wind components. In each case, the solid line, in this case, is a ground truth from large eddy simulations. And the solid black lines on the right 2 plots are also from large eddy simulations. And the green line is what we get from this physical model. And the key is that this is one model that captures all of those cloud regimes and boundary layer regimes in one physical framework with the same set of parameters. There's no switches back and forth and the like. So one thing we can also do, for example, is get the diurnal cycle, the transition from boundary layer turbulence, shallow convection to deep convection accurately in this form. Here's just an example of, well, one machine learning example that Tom showed yesterday, and it's worth saying a few words about it. So the dashed line was our physical guesswork. That's tedious. It's not fun to do, the guessing these functions. It feels a bit like dirty science, to be honest. It's just you make up stuff, and that seemed like a plausible physical story, and in the end, it's not very satisfying. So then we took this approach, well, what are the non-dimensional groups? What functions could we possibly get from these non-dimensional groups? And then we learned the neural network as a function of these non-dimensional groups and a linear regression model. And so red is a neural network, blue is a linear regression model. The vertical axis in this case is cloud liquid. Left is training in the present climate. And so this gave us something like a factor 2 or something more error reduction relative to our previous guesswork. And the previous guesswork was already really good compared to state of the art. I mean, this is something like a factor 5 improvement over state of the art. But interestingly, the linear regression model is just as good as a neural network in this particular case. It's, I think, one way of saying that if you reduce the problem correctly, in the end, you may not need very complicated models. And the right is just a warmer climate as a validation. It shows the same loss evaluated in the same sites in a validation case. And the key point is that the reduction in error is essentially the same as on the left, which is to say this generalizes to a warmer climate. So we trained it on the present climate because we learned universal functions that are reasonably well sampled in the present climate. You can use the same thing in a warmer climate. It's not holistic learning. Yeah.
So this was, when I see epochs, that implies that there's some sort of gradient. Is this a gradient-free training or a...
No, this is done with the same ensemble common inversion. The left is noisier because there's mini batching. The right is smoother because there's no mini batching under validation, but that's the only difference.
So what does epoch mean in this context? It's like, what is one epoch?
Oh, what's one epoch? It's, so you have there are various seasons of data and various years of data, and you just do what you do in your regular epochs. You mini batch from, say, one season, 1 year to the next, and so forth.
What's the 0 line, I guess, for aim at 4K?
Oh, this is just this is the error in Cloud Liquid.
Relative to.
Oh, this is relative to LES. This is all still on LES in a single column. So that's where we can do AMIP 4K easily. So these are LES driven by GCM output, and the GCM output is an AMIP 4K simulation. Yeah. Microphysics, again, similar things to what Marcus talked about. Here's just one example of a one-moment scheme, which has all the problems that Marcus mentioned, that there's a discontinuous transition from cloud to precipitation, which there shouldn't be. But the kind of interesting thing is, so those we trained with Lagrangian particle simulations, it's called super droplet simulations, and the top is the truth, and there's sort of a standard scheme in the middle, and after calibration of, in this case, just a physical parameter is the bottom, and what's shown is the condensate loading and the rain, and you see the standard scheme, it starts to rain too early, and then after calibration, it actually captures the particle simulations pretty well. So this was one example where just parameter calibration alone was quite successful in reproducing expensive, higher resolution simulations, which are not exactly a ground truth, but as close to a ground truth as we can get computationally. We have done this with two-moment schemes. And, we have worked with schemes that don't do this discontinuous separation of rain and precipitation, like what Marcus talked about, which I think is really the way to go, but it's not what's implemented here right now. So right now, this is implemented in a global model, global simulations. We run, I thought there was an animation, but it's not. Anyway, this is from a snapshot from global simulations with a cloud water path in this case. And after pre-training on LES, Lagrangian particle simulations and the like, what you want to do is actually fine-tune with observations. And here's just one example of what we did. We were interested in high-latitude clouds or mid and high-latitude clouds, so mixed-phase clouds. So we blanketed out the tropics, and in this case looked at short-wave fluxes at the top of the atmosphere. And the top is sort of the pre-trained model, and the bottom is after one round of fine-tuning. And the key thing is this fine-tuning, well, it reduces errors by something like 30% to root mean squared error of 10 watts per meter squared or so. And the errors are still plenty large over the Southern Ocean. There's plenty of room for improvement. We're not done here. But again, you can use, for example, to Marcus' point, can you train neural networks online? Yes, you can. So this is doing that. How to do it, good topic for conversation. It's not an easy thing to do this in this setting, how to set priors for neural network weights. We learned some lessons how to do it. I can talk about it. That turned out to be really important, but happy to talk about it after the fact. You can evaluate which parameters matter, and in this case, we looked at cloud radiative effects. So this is some proxy of how clouds respond to climate change. It has this model right now as a cloud radiative effect. Actually, look pretty similar to Model E, I think, order of magnitude, I would say. It's sort of middle of the road what climate models do. The key thing is that the parameters that are important for controlling the magnitude of this effect are, say, the ones that are in blue. And I know it's hard to read what's underneath, but I can tell you these are all parameters having to do with the entrainment of air between clouds and the environment, which is something people have found for decades over and over again. And then some microphysical parameters that also matter some. Again, just go down the list and have a quantitative way of assessing which parameters matter. You can do the same thing with observations. So here we did this with observations, including observations we wish we had but don't, like turbulent kinetic energy. There's in the decadal survey, there's a plan for a mission that would measure turbulent kinetic energy in a boundary layer. It would be very helpful. And perhaps unsurprisingly, the observations that we have and are most helpful are things like liquid water path, cloud liquid, all sorts of cloud parameters, humidity parameters, and the like. If you could measure entrainment, that would be nice. That's the most important thing, but we don't know how to measure it. It's a hypothetical observation. So all of that runs on a GPU native software system. It's all new code written in Julia. Julia was the right choice 6 years ago. if you start over, which I don't recommend, maybe you would use JAX, but I think ultimately it doesn't matter. There will be good AI agents that translates from one to another sometime soon anyway. But we use Julia, and I think it works well for us in that it gives us good performance. The performance is on par, say, with DOE's E3SM. It's a little hard to do apples-to-apples comparison, but it's within a factor of 2. The models have about the same throughput. And, well, it's way faster on GPUs than CPUs, which is unsurprising. What's nice is that it's a high-level language, so it's one language for the code, the performant code, and for analysis, here's just our continuity equation and the momentum equation. It's actually what it looks like in the code. It's pretty clean and simple, and makes it pretty easy to modify. And if you want to stick it in a neural network, well, there's an example of how to do it. Nothing complicated about it. It's very straightforward to do. It's running on GPUs, meaning that it's relatively inexpensive to run. And say, if you take dollar cost as the metric, relative to FP3 as just working with a company that uses this for weather forecasting, it's a roughly order of magnitude decrease in dollar cost for the same simulation. And I think we can decrease this cost by maybe another order of magnitude because there's a lot of performance on the table that we haven't optimized yet. Since the workshop title is Earth system modeling, I thought I'd just say something about other parts of the Earth system for just a few minutes. There's a land model that's modular, extensible, coded the same way as the atmosphere model. In fact, it uses the same compute engine underneath. And it's calibrated with satellite data in some examples I'll show. It's a pretty standard land model. It has carbon cycle model, it's a hydrology model, it has surface energy fluxes. I'm an atmospheric scientist. From my perspective, the job of the land is to provide surface energy fluxes to the atmosphere, so it does that. And I just want to show it to illustrate one point. There's always a question, well, where do you use machine learning and where don't you? And I don't think I have a general recipe, but here's an example where I think physics is not all that helpful, but machine learning is. This is snow modeling. So we still want a closed water balance, meaning we want to conserve the total water mass. So we have a conservation equation for snow, the snow water equivalent, SVI. It's just dSV dt equals precipitation minus melting, basically. Snow doesn't really move. It stays where it is. There's a little bit wind-driven things. It's not crucial here, right? And if you look at existing snow models, they're physical snow models, but they're really complicated. I spent some time trying to understand them. Lots of parameters, all sorts of interesting things. I like skiing. I'm interested in snow, but trying to build a physical snow model is hard. Now, we have measurement sites. For example, SNOWTEL is a US network. And what we did is we just learned an equation for the snow thickness, which is one of the key things you want to predict, thickness and heat flux through the snow. That's just d snow dt equals a neural network of whatever we thought could matter. Precipitation, temperature, humidity, you name it. And the nice thing about snow is that, say, snow in Mammoth Lakes is not in any fundamental way correlated with snow in Austria, except through correlations that are induced by common sources. It's entirely legitimate to hope that you can learn the relation between snow thickness in Mammoth Lakes or whatever, and hope that this translates to other parts of the globe. Not only that, we have measurement sites at different latitudes, different altitudes. They span what happens in climate change. Climate change means, a site that right now is a bit lower at the mountain will experience conditions a bit higher or a little higher latitudes. But we span what will happen in the future pretty well with the measurements we have right now. So this is very legitimate and works extremely well. Here's just an example. So these are neural ODEs. It's work by Andy Charbonneau. And the nice thing about learning the ODE rather than an autoregressive model is that, for example, we want to integrate in a climate model, we can do it then with any time step we want. So with 15-minute, hourly, daily time steps, well, Andy included a weekly time step. Not that you would want to do that, but in principle you could. It's a fairly straightforward neural network architecture on the right-hand side. Don't need to worry about the details, except to say it's important to impose some physical constraints of positivity of precipitation and such things, and melting is positive and the like. It is very simple to train once you get the data. It's extremely simple to integrate. It's literally a line in a code. And it achieves something like a 30% error reduction relative to some state-of-the-art snow models that are around. We have done the same thing for snow albedo, works the same way, works similarly well, and it's simple models, and this is one example where I think there's no use in trying to go too physical there. You just want to respect the conservation laws, but otherwise use the data where you can. Here's just an example. So the stars or the land model is actually 2 months old by now. It has gotten a little bit better. So the boxes and whiskers are existing land models from the ILAM intercomparison. Green is our land model for the key energy fluxes at the surface. And we're somewhere, well, up to 30% better or something, 10, 30% better than most models. And error is still decreasing. We're still working on the calibrations here. And the calibration, again, it's always a back and forth with model development. It's not just calibrating something. It's just, for example, you change the whole physics of stomatal conductance is one thing we changed that made fluxes better and the like.
So kind of similar to this is calibrated against like series or something, or station, or like.
So these are various data sets. So this particular case is actually against ERA. Series is not particularly good near the land surface. So here the reanalysis is more consistent because the problem is when any given data product you use, you get say series gives you energy fluxes. But what you don't get is a data product where all the energy fluxes add to zero as they have to. And if you use a reanalysis, it does it reasonably well. So it's an important constraint. But you could use other data. So that's where we are. I think the key thing for us that allows us to work reasonably rapidly is having this automated pipeline for calibration that can deal with noise effectively. It scales to high-dimensional parameter spaces. You can do calibration with hundreds of parameters we have done. Now, the ML people will say, well, what about millions? In principle, that should be possible. We haven't done it, but I bet it will get difficult once you get to really high-dimensional parameter spaces. It allows joint learning of physical parameters and ML parameters, which is, I think, crucial here for success, because in the end, you get correlations among parameters, and you do need to at least learn about them. And again, we are using this hierarchical approach, use process-level data where we have them. By the way, including for ice microphysics, we have used cloud chamber data as well, so laboratory data. Now, it turns out you have like 5 data points that are really useful there. It's pretty limited what you can do with it, but there's a little bit. And fine-tune it in the end with satellite ground-based data and global simulations. And we are still very much in the middle of iterating between calibration and developing the model further. Ideally, we'd like to be able to contribute to AR7, the next IPCC report, so that's coming up by the end of the year. We are pretty intensely working towards being able to do this. So I'll leave it at that. Thank you.